Pressure is the measure of force on a certain area. And how pressure is felt depends upon two things, on the force that you put and the area in which it is spread out or concentrated to. Of course, one way to increase the pressure is to increase the force. For example, if you have this finger right here and you're pushing up against a wall, you can push really hard on that wall and feel a lot of pressure at the point of your finger if you're pushing really hard. So, of course, one way to increase the pressure is to have a lot of force. But another way to increase the pressure is to reduce the area of pressure. For example, if I have my finger here and I'm putting the same amount of force I pushed up against the wall here into a thumbtack. Now, the area I'm not talking about is the head of the thumbtack. I'm talking about the point of the thumbtack. You're having all that same amount of force pushed into a smaller area. So when you have a smaller area, that means you have a larger pressure. And here's the formula for pressure. Pressure equals force over area. And it kind of makes sense. If you have a small number for area, say 2, then you can have a good amount of force. Say you have 100 newtons of force up here, and that'd have a pretty fair amount of pressure. But say you had a big area, 200 square meters, then that's whenever it'd be really have to have a lot of force. So here with the fingertip, you have a larger area than you have for the point of this tack, and as a result you can get more pressure in this case than you can in this case. Looking at my notes here. The unit for pressure is something called the Pascal, and you can see how it's abbreviated right here, spelled P-A-S-C-A-L. And there's a guy named Pascal that is the one that kind of came up with this. But anyway, a Pascal is newtons, which equates to the force, over meters squared, which equates to the area. And it is more important to know the pressure than it is to know the force. Sure, you can know you can have a lot of newtons of force, but it's got to be applied with that area to know the pressure. For example, here with a nail, you really have a potential with a nail of having a lot of pressure. But since you have so many nails, and since this kid who's laying on the bed of nails has so much surface area, then you really have so little pressure, because whatever the number would be here, I'm sure you could calculate it, would be a very large number. Same thing with snowshoes. Snowshoes, instead of having just the amount of surface area at the bottom of the foot, you have a huge surface area. I bet you're doubling or tripling your surface area by having these snowshoes. So as a result, snowshoes don't penetrate in the snow as much because snowshoes have a really big area. I mean, if this guy were just walking without the snowshoes, his feet would probably sink down in there. Okay, I think we have a calculation or so. Remember, pressure is force over area, and I believe that was newtons over meters squared. So you have the elephant that weighs 40,000 newtons. Stands on one leg during the circus performance. The area at the bottom of the elephant's foot is that many square meters. How much pressure is exerted on the elephant's foot? So we have pressure equals force over area. I'll just abbreviate that. So force is 40,000 newtons. And that would be over 0.4 meters squared. So in that case, it's just a matter of going to your calculator. I'm sure you probably could figure out something like that, but let's go with, see if I have this right, 40,000 divided by 0.4. I think that's right, 40,000 divided by 0.4, and sure enough, I hit the correct button. See, 40,000 divided by 0.4, cancel button. So 40,000 divided by 0.4, instead of hitting clear, let's go equal 100,000, and that would be in what? What unit? 100,000 Pascal. So that's a pretty, what seems like a pretty good amount of, well, it's PA right here, sorry about that. So it seems like a pretty good amount of force here. Well, let me see this number 100,000 again at some point. I forget whether it's this video or the next. I think it might be this video. Well, what about pressure in fluids? You know that fluids for the most part are air or water. Fluids can flow easily. What about pressure in fluids? Well, a fluid provides a constant pressure around any object in it. So say we've got this person who's a diver here. There's pressure over every part of the diver's body. So it's kind of a constant pressure, I guess you might say, over every part. So that's going to be the same thing is going to be true in air here. And what you're going to end up having is the net force. The net force is going to be kind of the sum total of all the forces against it. Not quite sure why I put a bunny rabbit here, but you have force over all parts of the bunny rabbit because air is a fluid. Checking my notes. The net force is produced on the surface of the object, whether it's in the air or whether it's in the water. The pressure that a fluid exerts depends on its density and its depth. Now, depth sounds different for air pressure and for water pressure, but I'll explain here in just a second. Pressure that a fluid exerts depends on its density and its depth. Let's take first of all the air pressure. You can see from this column we've got a mountain here, and there's a lot more molecules of air down at the bottom of the mountain. And as a result, you're going to have a lot more pressure at the bottom of a mountain. This person standing at the top of the mountain, you see not near as many molecules of air. So it's going to be lower pressure. Now, how much pressure is that going to be? At sea level, the air exerts a pressure on you equal to about 100,000 pascals. Hey, we have seen that term before. And where did we see that? That was in our example of the elephant standing on one foot. You know, that's a lot of pressure that's put on us, the same amount of pascals as an elephant put on one foot. So consequently, instead of using 100,000 every time, you're going to be referred to as 1 atmosphere. And we're not going to do it as much in this class, but you had a class in the 6th grade where you had like a measurement of, say, this is 1/2 of an atmosphere or 3/4 of an atmosphere. So that makes it for a lot simpler measurements there. So air density changes the higher you go. And how's that going to affect water? It's not quite as true in water about density, but it's going to be very true as far as depth. Let's go to another one here. Here's the ocean. Now, the farther down you go, the much more, you're not going to have as much density. What I mean to say is the density down here of the water is pretty much the same as the density up here. If you're in water, the water is not going to change density. It's not syrupy down at the bottom. It's about the same as it is at the top. But the depth is what the big thing is in the water. The farther down you go in water, the more water weight you have on top of you. The farther down in the water column, the more pressure you have. If you're a diver that is way down here at the bottom, you've got a lot of pressure on you. But if you're a swimmer who is kind of up in the water column, you don't have as much pressure on you. But even if you're pretty far up, you have a little bit of pressure. In fact, since water is heavier than air, diving just 10 meters down, that's 33 feet, and that's not much. I mean, you can go to local lakes and be 33 feet underwater. Just getting 33 feet underwater gives you about as much pressure as the entire atmosphere does. That's that 100,000 pascals. Just 33 feet of water. Can you imagine if you were 3,300 feet underwater? If you were 3,300 feet underwater, your lungs would collapse. Anybody that has to go down there is going to be having to have some kind of air or protection down there. You can't just get down there in a suit. Because of buoyant force, let's kind of shift gears here to go to buoyancy. Because of buoyant force, objects seem lighter in water. See, water has a buoyant force because objects thrust into water has more pressure on the bottom. Let's think about this. You have more pressure the deeper down you go. So remember I said water is heavy. So there's more pressure here than there is here. Interesting. So as a result, where will you get more lift? Where there's more pressure or where there's not more pressure? You're going to get more lift where there's pressure. So that's why sometimes things float in the water, because if you put a ball underwater, there's going to be more pressure underneath it than there is at the top. So that's why some things do end up popping up and floating. Now, not everything floats, but if an object is more dense than the fluid, it's going to sink. But if the object is less dense, then it has a chance and it will end up floating. Let me talk a little bit about Bernoulli's principle. Here I have a picture of a chimney. Bernoulli's principle, if it were really windy, would explain Bernoulli's principle a little bit better. Bernoulli's principle says faster moving fluid means less pressure. Faster moving wind means less pressure. So where there's high pressure down here, the wind blows from high pressure to low pressure. So if you have a lot of wind, the chimney will be sucked out of its smoke a lot quicker. Now this is especially true with airplane wings. This is an airplane wing. People make airplane wing to have air go fast over the top of the wing. The reason air goes fast is because Bernoulli's principle says that faster moving air has less pressure than slower moving air. So that would be less pressure up top and more pressure down at the bottom. And since it goes from more to less, then that would give it lift. Less pressure up top. Take a look at this prairie dog mound. You have prairie dog mounds, they have higher elevation at one place than the top. So it's going to be windier here. Since it's windier here, you have less pressure. You have higher pressure here, and you may remember that wind blows from higher pressure to lower pressure. So because of Bernoulli's principle, these prairie dog holes actually have some kind of breeze flowing through it. And that might be something you can remember. If you can get some kind of hole at a windier place, then Bernoulli's principle kind of picks in. And finally, Pascal's principle. The pressure exerted on a confined liquid is transmitted equally in all directions. Now, you got a couple of diagrams here, but I think I have better ones here. So if you put pressure on this fluid right here, let's say it's some kind of liquid, the same amount of pressure comes up through here and it doesn't reduce. So as a result, you could actually lift up a car. Hydraulic lift will lift up a car. If you put pressure here, then you're actually able to lift up a lot right here. That pressure is transmitted through the fluid with equal strength. There are hydraulic jacks which can lift up a car, and you just put the amount of pressure here just to lift it up, and it really lifts up the heavier object right there. Hey, I hope you've learned a little bit about pressure.